We saw that the Lagrangian points L1 to L5 are equilibrium points. But it's not enough to know that a number of equilibrium points exists for a dynamical system. We also needed to determine the stability of such points. For that, we needed to do a stability analysis to examine the behavior of a particle that is given a small displacement from an equilibrium position and check if this displacement is going to grow or if this displacement is going to oscillate around the equilibrium position. What I'm going to do is to linearize the equations of motion and carry out this linear stability analysis. So these are the equations of motion. The second derivative of x minus the Coriolis force is equal to the derivative of the potential, and the same thing for y. Let's use units such that the mean motion is equal to 1. So the equations of motion are, let's consider an equilibrium point, x naught and y naught, and consider a small displacement around them. Let's call this small displacement capital X and capital Y. So we can substitute these equations into the equation of motion, and therefore around the equilibrium point, we have pretty much the same equations, but only for the small displacement. Let's expand now the right-hand side, the derivatives in Taylor series. So this is du dx at the equilibrium point, plus x times the first derivative in x of the function, which is du dx, plus y times the derivative in y of the function, again, which is du dx. And same thing for Taylor expansion in y, du dy at the point 0, plus y du dy of the function, du dy, plus x times the derivative in x. All of these at the equilibrium point 0. Now recall that the equilibrium points were found by solving the equation du dx equals 0 and du dy equals 0 at the equilibrium points. So these first terms here cancel, and what you have then is plus terms of higher order in x squared, y squared, or xy that we're not interested in because these displacements are infinitesimal. Now these quantities are all constants because they are evaluated at a specific point. So let's substitute them by constants. Let's call them uxx is equal to the second derivative of u with respect to x at the point naught. Uyy is the second derivative of u and y, also the equilibrium point, and uxy, this last derivative. With that, then the equations of motion become, now let's put this in matrix form. And to find the solution, we need to find the eigenvalues of this matrix. Let's define then the coefficient matrix A, and the solution is that the determinant of A minus the eigenvalues times the identity matrix is equal to 0. So this leads to the characteristic equation, which is a biquadratic. So you can solve this for lambda squared, which makes it relatively easy to find the four roots. The four roots are lambda 1 and lambda 2, and lambda 3, lambda 4, the same except that the second term has a positive. The general form of these eigenvalues are, for lambda 1 and 2, is plus minus j1 plus I times k1. And for lambda 3 and 4, it's plus or minus j2 plus I times k2, where I is the imaginary number, j and k are constants. And the solution can be written in terms of a linear combination of these eigenvalues. Define, say, a coefficient alpha. It's a combination of exponential of the four eigenvalues. So you can see that if you put these eigenvalues, the form of these eigenvalues, a real number plus an imaginary number, on the solutions for x and y, if j is not equal to 0, then you have an exponential of a real number, you have growth. Whereas if you have j equals 0, then the real exponential is going to be 1, and you only have an imaginary exponential, which means an oscillatory function, so you have oscillations. Now this x and this y, they are the displacements around the equilibrium point. If the displacement grows in time, then you have an unstable point, means that the displacement keeps growing. A little displacement is going to lead to more displacement. It's an unstable equilibrium point. Whereas if you have only oscillations around the equilibrium point, then you have a stable equilibrium point. So this is how we check the nature of the equilibrium points, if they're stable or unstable. Now let's apply now this to the Lagrangian points and see which points are stable and which points are unstable.